In this video, we will be looking at an introduction to probability theory, and specifically we will introduce the idea of discrete and continuous random variables. So, probability is a mathematical framework for representing uncertainty. Wherever you have some uncertain outcome, we tend to use probability as a mathematical representation of the uncertainty in the problem. So, in engineering systems, we have multiple sources where such uncertainty occurs. Sometimes we have inherent randomness or stochasticity more specifically in the system. For example, in quantum mechanics, the laws themselves actually lead to some amount of randomness, okay, or uncertainty. Or let us say you are dealing with a pack of cards, you have a little bit of randomness thrown in there. So, in such cases, whenever you try to predict something, you are going to have probability theory coming in. Now, we can look at a slightly higher level of abstraction, where you might have deterministic systems that is the laws themselves are actually not random, unlike quantum mechanics, but you might have incomplete observability, okay, which is you are not able to see all that is happening in the system. For example, if you have a macroscopic description of let us say flow in a room, we know that inherently there are molecules and within them atoms, etc. We are not able to observe them, and typically this leads to a little bit of uncertainty in the properties. Okay. We know that macroscopic properties are defined or derived from microscopic properties, but this is done so actually probabilistically, even though in real life we do not treat them as if they are probabilistic. You have multiple such examples. Whenever we have incomplete observability, once again you can use probability theory. A third level of abstraction is you might not have randomness, you might even have in some sense complete data, plus you might have deterministic laws, but still despite having full data you actually have an incomplete model. The model can be incomplete, as in let us say weather models. So, you do not deliberately you do not use all of the data in order to either get simple models or tractable models. In all these cases in engineering you will typically use probability theory. Now, our interest of course is we want to use probability ideas in machine learning, and there are two primary uses of that. First is in constructing learning systems themselves. By a learning system I simply mean a machine learning model. Okay. So, you want to construct a model. So, if you try and mimic let us say human reasoning about uncertainty, we say the probability of rain is probably 60% tomorrow. So, inherently even within our models there is some probability built in. Okay. So, in order to incorporate such probabilistic thinking, you have probabilistic models. So, notice this, you can have probability built in right into the model itself. Okay. So, that is one way of using probability. Another idea is you might actually have a deterministic model. Okay. For example, as we will see, many neural network models are almost by design they are deterministic. So, you could have a deterministic model that is how the input relates to the output is actually a deterministic process. Nonetheless, the output itself can be analyzed probabilistically, because the learning system is only correct part of the time, it is not correct all the time. So, for example, if you might see a Google image analyzer or any other image analyzer, typically the actual output in the algorithm, as we will see later on in the course, will not be a specific class. It will not say this picture is a cat deterministically. What it will say typically is something like this picture is a cat with probability 0.9. So, this would be something like an analysis of the learning system probabilistically. It might go wrong 90% of the time, stuff like that can be analyzed probabilistically. This is a probabilistic analysis of even deterministic or even probabilistic models. When we come to probabilistic analysis, there are two interpretations of what a particular probability means. Now, all of us know probability lies between 0 and 1, but there are two large schools of thought, they often come into philosophical fight. We will not get too much into that in this course at least, but just for a brief introduction, if you take a statement such as there is 60% chance of rain tomorrow, this can be interpreted in two distinct ways. Okay. So, one way is what we are usually used to, this is called a frequentist model. Frequentist model would be something like, okay, so the temperature today is this much, the pressure today is so much, it is slightly cloudy, and in all such cases before, when such things happened, in 60% of the times it rained. So, such a statement would depend on, let us say, something like what you have observed so far, and that is a frequentist approach to probability. Okay. It says it depends on the proportion of events in an infinite sample space, as we will see shortly. Okay. It is typically an objective measure. Okay. So, if I say what is the probability of a fair die throwing up 2, you will say if I throw this dice, let us say millions of times, 2 will come up about 1/6 of the times. So, the probability is 1/6, this is an objective measure. The second measure is called the Bayesian approach, okay, preferred typically by economists or even philosophers. Okay. So, this actually measures degree of belief. So, if somebody says that there is a 60% chance of rain tomorrow, what they mean typically is it looks a little bit more than 50-50. Okay. So, it looks kind of likely that I am going to get about rain a little bit more than, but I am not very sure. So, something of that sort, it is a rough estimate, that is something like a Bayesian. Of course, there are more technical meanings, it is not as bad as what I am making it out to be, but it is a subjective measure. So, there is a certain amount of degree of belief in this statement that is incorporated in a Bayesian. Now, for our purposes, we do not really strongly care, in a couple of places we will make this distinction, but other than that we do not really strongly care about which approach we are taking, because whatever probabilities result out of this, the mathematics works exactly in the same way. For example, if a doctor says to a person your probability of getting disease 1, let us say heart attack is 0.1, and probability of getting disease 2, let us say foot ache, is 0.2. Okay. Let us say that these two diseases are independent. Okay. This is important in the example I am using. Now, regardless of which interpretation of probability you choose, it is always true that probability of disease 1 and disease 2 will be, if the events are independent, you are going to get 0.1 multiplied by 0.2, which is 0.02. This is regardless of whether it is a frequentist approach or whether it is a Bayesian approach. So, the mathematics of probabilities work exactly in the same way regardless of which approach we choose. So, we will stick to choosing between frequentist and Bayesian depending on what makes sense, and we will only look at what the mathematics of the resulting probability is. So, let us come to a few definitions which we will be using. The first is the definition of a random experiment. The simple definition of a random experiment is you do an experiment and it results in different outcomes each time, despite you having similar conditions. For example, I toss a coin, it seems to me that I am keeping this coin exactly in the same way and my thumb in exactly the same way, and yet sometimes you get heads and sometimes you get tails. Okay. Such an experiment is called a random experiment. So, rainfall amount or throwing of a dice, infinite examples of this. The second definition is that of a sample space. Okay. So, suppose you do a random experiment, all the possible outcomes, the set of all possible outcomes of this random experiment is called the sample space. For example, if you toss a coin, the set of all possible outcomes is you either get a heads or you get a tails. This would be if you are tossing a coin once. Now, suppose I toss a coin twice, then the sample space is heads heads, heads tails, tails heads or tails tails. Okay. So, this would be my sample space now. One of these 4 should have occurred when I tossed the coin 2 times. Now, what is important is that the sample space which we use for determining probabilities depends on actually the purpose of analysis. So, the same event can be described in many different ways. So, let us say we have manufactured a pipe and we want to, and knowing that manufacturing has certain uncertainties built into it, you are not always going to get a pipe of the same size each time. So, we can call this a random experiment. So, what I want to describe is the sample space of what kind of pipe did I get. Now, depending on the purpose of my analysis, our sample space S could be either S is R plus means the positive half of the real number line. So, this is simply S is some number which is positive, all of us know this. So, all we are saying is the diameter could lie anywhere between 0 and infinity. This is one sample space. Another possible sample space is the diameter of the pipe was low, or it was medium, or it was high. Okay, suppose we are only interested in whether it is in one of these three. Is it too small, is it kind of okay, or is it too big? If these were our only three interests, quantities of interest or qualities of interest in an analysis, our sample space would be simply this. Okay. Or we could be basically interested in, is it a satisfactory pipe for my purposes or unsatisfactory. So, then my sample space simply has two elements, satisfactory or unsatisfactory. The point is that you can describe the outcome of the same event in many different ways depending on which way you wish to analyze it, and as an engineer often later on when we make machine learning models, this becomes an important part of what role you play describing the sample space. We come to a very important quantity, this is a fundamental quantity often while using probability theory, the idea of a random variable. So, it is useful typically to denote the outcome of a random experiment by a number. Now, notice for example, if I toss a coin, my outcome, my sample space for example was either heads or tails. Heads by itself is not a number, tails by itself is not a number. Okay. You could assign a number to it, for example, you could assign the number 1 to heads and 0 to tails. Okay. So, then if you assign one number, for example, you could even have categorical outcomes. For example, I take an image, I ask is this a cat, a dog, a horse, or a picture of a cow. So, then you have 4 possible outcomes. Again, cat, dog, house, cow, horse, cow are by themselves not numbers, but you can assign numbers, for example 0, 1, 2, 3 or 1, 2, 3, 4 etc. Okay. So, you can even assign numbers, numerical to categorical outcomes. Okay. So, the variable that associates a number with an outcome is called a random variable. Okay. So, please notice this, a random variable by itself is something that is mapped to either a real number or the integers etc. etc. Notation, this sometimes gets confusing for students. So, please remember this, the variable itself is denoted by a capital letter. For example, capital X would denote a random variable, the variable itself. Its value is denoted by a small number. For example, if I say x equal to 0.5, x is the random variable and 0.5 is the value that it takes. Let us take another example. Suppose we want to find out the rainfall on a particular day. So, this is a random variable, as you know we cannot say for sure what the exact amount of rainfall would be. So, let us call this random variable capital R. The amount of rainfall would be actually denoted by small r. So, suppose I want to make the statement, what is the probability that the rainfall is greater than 10 mm. So, I want to see how to denote this or what is the notation I would use for this. Remember, probability is denoted by P. The amount of rainfall as a variable is capital R. The actual value it takes, which is 10, is denoted by small r. So, we would write something like, the mathematical notation is, what is the probability that the amount of rainfall is greater than 10 mm. So, P R greater than 10. Okay. So, suppose I ask what is the probability that the dice gave me the number 3, I would, and if x was denoting the random variable which gives you the output of the dice, you would say something like probability that x is equal to 3. So, suppose you have a uniform random variable. A uniform random variable is one where all the outcomes are equally likely. For example, you have an unbiased coin, if you throw it, you either get a heads or a tails with a probability 0.5. So, the probability distribution is called a uniform distribution. Similarly, for a dice, you could have a uniform distribution again. Okay, so, let us come to probability distributions. A probability distribution tells us how likely a random variable is to take each of its possible states. So, remember, a random variable can take any state depending on what the sample space is. If the sample space has 10 members, then the random variable can take all 10 values, any of the 10 values, not all 10 values simultaneously, any of the 10 values. The probability distribution tells us that not all of them might be equally likely, some of them might be less likely, some of them might be more likely. So, that probability distribution is what tells you how likely each one of these values is. So, depending on what kind of variable we are dealing with, we might have two different types of probability distributions. So, a very common probability distribution is that of a discrete random variable. A very common random variable type is a discrete random variable. This has a finite or countably infinite number of possibilities. For example, if we look at the number of errors in a particular page, or the number of errors I make while speaking, or the number of errors that the doctor made in diagnosis, all these are actual numbers. Okay. So, these are finite, the range of that the random variable can take is actually finite. Okay. So, these are discrete random variables. Now, more importantly, the probability is measured by what is called a probability mass function, as we will see in the next slide. So, we can have a continuous random variable also, which has a real number interval for its range. Okay. An example would be any real number random variable such as temperature, pressure, voltage, current, etc. Okay. In such a case, the probability is measured by a probability density function. Please notice the difference. For a discrete variable, it is a probability mass function. For a continuous variable, it is a probability density function. Okay. So, let us come to a probability mass function. Once again, it is done for a discrete variable. We denote it by PMF, standing for probability mass function. Okay. All it is a list of possible values. Okay. So, if the random variable takes multiple values, it is simply a list of those values along with their probabilities. So, let us say you have a biased dice. A biased dice means not all 6 sides are equally likely. So, 1 is somewhat likely, 2 has a different probability, etc. So, let us say we have these 6 probabilities. Notice how I am denoting this. All I am saying is P of x equal to 1 equal to 0.1, etc., etc. You will see that this should be actually 2, please excuse me. So, P of x equal to 1 is 0.1, P of x equal to 2 is 0.1, etc. You have to give a probability for each possible outcome in the sample space. So, for example, if I take a graph and have this 6 possibilities drawn here, which is the sample space, please remember this is x, then probability that x equal to 1 is 0.1, 0.1, 0.2, 0.2, 0.2, 0.2. So, this essentially is the probability mass function. Okay. Some of you might notice that this looks like a point load, which is exactly true. In structures you might have seen something of this sort, a point force applying at a single point. So, that is what a probability mass function is analogous to. Okay. So, in order for a probability mass function to be a valid probability mass function, it has to satisfy certain criteria. One thing is you have to make sure that the domain of P is the set of all possible states of x. All that means is that P should have some valid value for each output for x. For example, if I do not give, let us say these two values and say that P is valid only from 1 to 4, then this is not a valid probability mass function. My whole sample space must be covered. Next, of course, all of the individual probabilities, since they are probabilities, have to lie between 0 and 1, they have to be non-negative as well as they have to be less than 1. Finally, we know that the whole sample space So, since one of these x should definitely occur, the probability summation of individual probabilities has to be 1. So, using these laws you can immediately come up with the fact that for a uniform random variable, which is a random variable where all the outcomes are equally likely, if there are k outcomes, okay. So, x I goes from 1 to k, then a uniform random variable, each of those probabilities will be equal to 1 by k. Okay. So, as I said earlier, this is analogous to a point load. So, let us now come to continuous random variables. Remember that instead of a mass function you now have a density function, okay. D stands for density. What it is effectively is a probability per unit length. Once again you can make an analogy. So, instead of a point load you now have something like a distributed load. Since this is a continuous function, we do not have gaps between any two random variables. What we have is a continuous distribution, and instead of giving probability at a point, what we will give is probability per unit length, or in other words probability density. This is like a distributed load. So, let us say R is the amount of rainfall and I want to find out probability that the rainfall lies between 10 and 20. Okay. As it turns out, the probability of any particular point is irrelevant. What you look for is probability in a range. So, let us say you want to find out the probability that the rainfall is between 10 and 20. Okay. In that case, we simply denote it by P 10 less than equal to R less than equal to 20. These two are equivalent because probability of any exact specific value is effectively 0. The area of a line is effectively 0. So, this probability can be given by area under this curve, just like for a distributed load, load can be given by area under the curve. Okay. So, if you do not understand that analogy, even then you can immediately see that each of these probabilities, when they sum up, if it is probability per unit length, then this area is given by integral of p of x dx between 10 and 20. Okay. So, in general the probability that A will be given by integral between A to B p of x dx. So, in order for P to be a probability distribution function, the domain once again just like last time has to be all possible states of x, okay, and probability density has to be positive. Notice that it is not necessary for the probability density itself to be less than equal to 1, because this is a density. Okay. So, let me show an example. So, let us say my probability density function looks like this, it is a hat function. Let us say this is 0, 0.5, then this value, this area has to be 1, therefore, this height has to be 2. Okay. All I am interested in is in making sure that the area of any sub portion has to be less than equal to 1, because it is the area which is the actual probability. This small p of x on the other hand is the density. Okay. What it is probability per unit length. So, I can arbitrarily make this large by simply reducing the length, okay, for the same probability. Our condition here is of course that integral of p of x dx has to be equal to 1. An intuitive way of thinking about the probability density function is to think of it as a normalized histogram. Okay. So, suppose I take a random number, okay, which lies between let us say -5 and 5, okay, and I take 10,000 such random numbers. So, let us say here is the histogram that is drawn. Okay. Notice these values here, this value is 800, this value is 100. So, somewhere at around 0 we get a lot of hits and everywhere else we get a low number of hits, we can draw a histogram. Now suppose I normalize this. By what I mean by normalization is, instead of looking at number of times I got a 0 or number of times I got a value between, let us say, minus 0.1 and 0, instead of doing that I start looking at what fraction I got. So all these numbers, if I divide them by 10,000, what I now get here is 0.08. Okay. So I had 10,000 tosses which went between minus 5 and 5. So now I divide all these numbers and I look at fractions instead of actual numbers. You see that they form a curve of this sort. Now suppose I keep on increasing my tosses, you might kind of guess that slowly but surely it will start converging to some nice bell curve. We will see this later on this week. Such a curve will usually be a Gaussian curve, but it will usually converge to some sort of curve. That curve would be the probability distribution function, not for a finite number of throws, but for an infinite number of throws. A normalized histogram tends to a probability distribution function. Thank you.